Today, we're going to be making bread. I'm going to be adding 3 cups of flour mix. This flour mix already has salt, sugar, and milk powder added. Now, a packet of yeast is added and mixed in. This yeast is a fungus that will later ferment sugars, producing ethanol and carbon dioxide as byproducts. One tablespoon of butter is added to 1 cup of water. This is going to be microwaved around 40 degrees Celsius in order to dissolve the butter. Now the butter and water are added to our flour mix. Mixing is continued until the dough comes together. The dough is now a cohesive, slightly sticky mass. When the dough is together, it is now time to knead. The dough ball is placed on a surface that is floured to prevent sticking, and kneading continues until the dough is smooth and elastic. This indicates a change in some chemical interactions. After kneading, the dough ball is left to rest for 10 minutes while covered. After the rest period, we see that the dough has risen. This is because the yeast have digested some sugars and produced carbon dioxide within the dough ball. The dough is now flattened into a rectangle around 12 inches by 7 inches. Starting from the short side, the dough is rolled into a log and the ends are pinched closed. I'm going to pinch the edges of this bread roll together and then put it in the bread pan. Then I'll allow it to rest for 45 minutes so that it can expand. The dough has around doubled in size and is now ready to be baked. This will happen at around 400 degrees Fahrenheit or 200 degrees Celsius for around 30 minutes or until the bread is golden brown. Now the bread is ready to eat. Now that we've made bread, we are ready to explore its chemistry. When making bread, one of the most important steps for good texture is the formation of gluten sheets. To understand what these are, let's first learn about the components of flour. Flour has small starch granules with different proteins. Starch is a polysaccharide of glucose existing in 2 main forms, linear amylose and highly branched amylopectin, which has a molecular weight 10 to 20 times that of amylose. Proteins are also present in flour. Most flour for bread making contains at least 12% protein. The extremely large proteins involved in forming gluten are water-insoluble and are broadly sorted into 2 types, gliadins and glutenins. Gliadins have high molecular weights between 28,000 and 55,000 grams per mole. Glutenins are composed of multiple proteins and may have overall molecular weights around 2 million grams per mole. These water-insoluble gluten proteins may have many amino acids with hydrophobic regions, but especially they have glutamine. Glutamine can form additional hydrogen bonds between protein strands and with water because of its amino group with lone pairs on a carbonyl. And this greatly affects the strength of the gluten formed. Over here, we have a generic protein with hydrogen bonding. This hydrogen bonding shows an interaction that might typically happen between gluten chains. After adding water and mixing, the dough appears much different. When water is added to flour, proteins hydrate, expand, and form gluten, a matrix that holds the starch granules that make up most of flour. Along with the hydrogen bonds that amino acids like glutamine can form, some protein chains also have thiol groups. These are from the amino acid cysteine and form covalent disulfide bridges that hold polymers together. Interactions occur when water is first needed, but when water is first added, but kneading increases the strength of interactions to increase dough strength. Initially, the wheat proteins have little order. As dough is kneaded and stretched, the proteins uncoil and line up in chains to form gluten sheets. This increases the amount of intermolecular bonding, increasing the elastic strength of the gluten matrix and allowing for better trapping of carbon dioxide produced by yeast. In addition to increasing flavor, the salt that was added earlier has a binding effect on gluten. since its ions shield the charges on gluten from one another and allow protein molecules to come together more closely. This again makes the dough stronger and better able to rise. During the rising process, yeast uses enzymes called amylases to break down starch. With smaller glucose monomers, yeast can perform fermentation. It can reduce carbonyl groups to hydroxyl groups, so it produces ethanol and CO2 as waste products. Other flavorful byproducts like acids and amino acids are produced. After baking, we see that the color and texture of the bread have changed. The dough goes from slightly dense and stretchy to an airy sponge. In the cooking process, gases heating up within the dough expand, creating larger air pockets in the gluten matrix. The starches in the flour gelate or absorb water around 60 degrees Celsius to 82 degrees Celsius. At 60 degrees Celsius, the yeast has also died off. Proteins in the dough denature at higher temperatures, meaning their chemical structures are degraded and their interactions with each other change. The color change of the crust is due to caramelization and the Maillard reactions. Caramelization occurs at a lower temperature than the Maillard reactions. It is due to starches being broken down to simpler sugars with heat exposure, above 300 degrees Fahrenheit or 150 degrees Celsius for glucose. Browning occurs as condensation and isomerization reactions happen. Here is one sample caramelization. This is just a sample reaction and one of many different caramelization reactions. The Maillard reactions occur between 280 to 330 degrees Fahrenheit, or above 140 to 165 degrees Celsius. When sugars or starches are heated with proteins or amino acids, brown polymers are produced by a wide variety of complex reactions. For the Maillard reaction, simple reducing sugars are required. These have hemiacetals or open-chain forms with an aldehyde group, like this open-chain maltose that you see. The first step is the formation of a compound called N-glycosylamine. This forms with the carbonyl group of the reducing sugar reacts with the free amino group of a protein, causing loss of water and product formation. After glycosylamine formation, an intermediate is formed and isomerized, a process called the Amadori rearrangement. The result is a ketosamine. As a third step, ketosamines can react multiple ways. One way is dehydration, or loss of two water molecules. The resulting products are called reductones and dehydroreductones. These are also caramelization products. A second reaction is fission with water to form products like diacetyl acetal or pyruvaldehyde. These products can become aldehydes through the Strecker degradation with amino acids. They can also undergo condensation to aldols. A third reaction involves loss of three water molecules, producing a Schiss base. Then the compound reacts with amino acids and water to form melanoidins, which can give both pleasant and bitter flavors.